So welcome, ladies and gentlemen. Today, our goal is to understand the unit circle and some of the trig properties that we can use in conjunction with the unit circle to solve trig problems, to produce trig identities, and solve trig equations. So the first thing I want to do is refresh these special right triangles, because these are the kernel of it. How does the ratio sets in a 30-60-90 triangle come about? Well, if I take an equilateral triangle, let's say that each side is exactly 1 unit long, do we know what these angles are? 60, 60, 60. And if I were to then drop an altitude, what I produce is right triangles. And since this angle is 60 and this angle is 60, that means this has to be bisected to produce 30-degree angles, such that I'm now looking at those 30, 60, 90 triangles. And these two triangles are congruent. They're congruent because they share this side. They have reflexive sharing this side. They have right angles. So by RHL, these two triangles are congruent. Since they're congruent, we know by CP, CTC, that these two parts are congruent. That means if the whole length was 1, each part is how long? Right, 1/2. So if I'm now looking at just one of these triangles, which is our 30, 60, 90 triangle, what we see is that this side is 1/2 and this side is 1, and we don't yet know what this side is. But we can solve that. We can use the Pythagorean theorem to say that 1/2 squared plus the question mark squared equals 1 squared. So that means 1/4 plus question mark squared equals 1, which means question mark squared equals 3/4. If I square root both sides, I get the question mark no longer squared is equal to plus or minus root 3/4, which I can treat as plus or minus root 3 over root 4, which is plus or minus root 3 over 2. And because we're talking about a length here, absolute length, we're going to forget about the -1 for now and just focus on the positive. In other words, we can see that in a right triangle with 30, 60, 90, the ratio of the sides falls in this relationship. And because any other triangle that is similar to this one, in other words, 60, 30, 90, but now this side is 10, how long will this side down here be?
1.
Sure, it's going to be half as much. And then how long would this side here be? If I take this one and double it to get here, I take this one and multiply it by root 3 to get here. So what would be this side length?
5, 2.
Good. And so we learned about this in geometry. And we know then that the ratio of the sides of a 30, 60, 90 triangle fall in this relationship, 1, 1/2, and root 3 over 2. And I'm going to look at the triangle from this perspective as well. It's still a 30, 60, 90 triangle. How long is this hypotenuse going to be?
1.
How long is the side opposite 30 going to be? And how long is the side opposite 60 going to be? Now, the whole point of this is that if we can look at a unit circle, and why do we call it a unit circle? Yes, we're saying that the radius of this circle is exactly 1 unit, which means as I come out here along the 0-degree mark, the coordinate at the end is what? What's its location on the XY axis?
0, 1.
Close.
1, 0.
1, 0. Right? It goes out that distance of 1, which is our radius, and it doesn't go up at all. What about this point up here? Good. And how many degrees do we see this as? Tyler's carrying you guys. All right. What about over here? Somebody new, give me this coordinate.
-1, 0.
Thank you. And what's our degrees there? Good. And down here, what's our coordinate?
0, -1.
Yep. And if this is 90, 180, what degrees is this? 270. Now, notice that I did all of those 90 increments first. Now what I'm going to do is I'm going to take a look at all of the triangles that are like this. Okay. Because this is which of our three triangles? Is it a tall 30, 60, 90, an isosceles one, 45, 45, 90, or a wide 30, 60, 90? Sure it is. So that means this angle is 30 degrees, which means this coordinate reflects 30 degrees. And let's fill in the side lengths. We don't really need to put in the hypotenuse because we know it's always 1. But how long is this side? Good. And if that's 1/2, is that the y value or the x value of this coordinate?
Why?
Well, because we're trying to ensure that we know what the coord. Just kidding. Okay. And this is √3/2. Well, there's only 3 math jokes. Let me use them when they come up. So what is this, the y or the x? So that comes up here, and I can call this √3/2. And this coordinate becomes really important to us. We'll find that, for example, if I want to evaluate the sine of 30 degrees, I can use this to do that. We'll talk about that in just a second. But to build the unit circle, I want to see if there's another wide 30, 60, 90 triangle in here. And looks like I can't see it as well, but it's here. And if this goes 30 degrees up from 0, then that means it goes 30 degrees back from 180. So what's the degree measure here?
150.
Yeah, 180 minus 30 is 150. And then again, what's our x component? Is it the long number, √3/2, or is it the shorter number, 1/2?
Oh,
Long one, √3/2. And then the altitude part is 1/2. So my coordinate here is √3/2, 1/2. But because I'm in this quadrant, which has gone negative, my x or my y? So in other words, this is really negative √3/2. That's my x value is negative √3/2. Do you see any other places where we could have 30-degree angles that are, excuse me, wide 30, 60, 90?
60.
Well, 60 is a 30-degree triangle, but it's not the wide one, it's the tall one. But we have one here and one here. Good. So if 180 is this part, and we know we're going 30 degrees more, we can find this by adding it. 180 plus 30 is 210. And then again, we see that it's got this same x value of negative √3/2. And now the y value is still 1/2, but because it's going down, it's negative. Negative 1/2. And the last one over here, if this is 0, it could also be considered 360 degrees. As we wrap all the way around in the circle to 360, we're coming back 30 degrees worth of that. So what's our angle measure here?
330.
Sure is 330 degrees. And here we've got an x value of positive √3/2 and a y value now of negative 1/2. What do you think? 5. Okay, I could do those triangles, just the wide 30, 60, 90s. I could draw those if I needed to. 3 makes sense, but I can't really remember that. 1, that doesn't make sense to me. Okay, good. So now let's do the second part. Let's do the tall 30, 60, 90s, this one. Because it's the same triangle, it's just oriented differently. So what's my x value now?
1.5.
Good, 1/2. What's my y value? root 3 over 2. Which means up here, this coordinate is going to have an x value of 1/2 now, and a y value of root 3 over 2. Excuse me. And as we reflect this over here, this is still going to have the shorter x value and the longer y value. So this coordinate will be negative 1/2 positive root 3 over 2. And if we went up 60 degrees to get here, what's 60 degrees shy of getting to 180?
120.
Yep. So this is 120 degrees. There's another tall 30, 60, 90 down here. What would be the degree of that? We're at 180, we're going 60 degrees further. 240. And what's our x value? Tyler, don't say it. What's our x value down here? Good. Negative root 3 over 2. Okay, would you guys all please fill in the next one here by yourselves? We got 1/2 negative root 3 over 2, right? All right. Last piece for us to fill in the coordinates is to look at an isosceles 45, 45, 90 triangle. So let's remember how that comes about. If we begin with the square and we slice it with the diagonal, we produce a relationship that is 90 degrees. These have been bisected, so they're 45, 45. This is isosceles, and we'd have to find this length. Well, I know 1 squared plus 1 squared would have to equal that length squared. So that's 2 equals squared. So root 2 equals question mark, again, plus or minus, but we just choose the positive. So this is root 2. So that tells me that when I've got a 45, 45, 90 triangle, the ratios are this, 1, 1, and root 2. Why will this not apply to our unit circle?
That is the hypotenuse.
Good. We need to scale this triangle down, similar triangle, to make it hypotenuse of 1, which means we'll divide all sides by root 2. That makes our hypotenuse 1, which is fine. Can I leave this as a side length, 1 over root 2? Oh, I need to rationalize that. How do I rationalize 1 over root 2 over itself? Excuse me, root 2 over regular 2. And so this gives us what we want for our isosceles 45, 45, 90. So everybody enter this in, please, with 1, root 2 over 2, and root 2 over 2. Which means every time we're dealing with a 45-degree angle, it's really easy because the x and the y are the same value. So here in this middle triangle, what are the coordinates going to be? And that's 45 degrees. And over here, to come back from 180, 45 degrees is 135. And we know the values are root 2 over 2. Which one's positive, the x or the y?
Why?
Yep, y is positive. The x is now negative. And then we come down here. This is now 185 plus 45, which is 225 for our angle measure. Root 2 over 2, root 2 over 2. These, in this quadrant, they're both negative. Then we come over here and now we're at 360 minus 45, which is 315. We get root 2 over 2, negative root 2 over 2. All right, so in my mind, there are 3 parts to the unit circle. The first is knowing the angle measures as you work your way around. And it's not a linear, broken up, same slope kind of thing. It goes up 30, then it goes up 15, then it goes up 15, then it goes up 30. Then it goes up 30, right? It's not evenly distributed. So you have to remember that the 30, 45, and 60-degree angles. The second part is the coordinates that we talked about coming from the similar triangles, special right triangles. What's the third part? Come on, this is the new one.
Something other stuff.
Nope, radians.
Oh.
So how do we do radians? Well, we can do it the exact same way I talked about doing the angles. If I can translate, or I would say memorize these 3, maybe these 4, it gives you the rest. So if I take 30 degrees, I could translate that into radians by multiplying by pi over 180. That gives me pi over 6 when I reduce. So I know that this measure as a radian is pi over 6. Now, over here, what's the radian measure equivalent of 180 degrees?
2 pi.
Almost. Just pi, right. The whole circle is 2 pi. Actually, I should make that a 0 and then 2 pi below it. So if this is pi, but I'm actually looking for something involving sixths, because I'm going to do these green triangles first. How many sixths are in a full pi? Right. I could treat this as 6 pi over 6, couldn't I? So when I go back 1, I'm subtracting 1/6 from 6/6. What's the radian measure here? 5 pi over 6. Not 6 of them, because I subtracted 1. So now I've got 5 of them. No. But what about going down here? We're just talking about the green triangles now. If I was at 6 pi over 6,
7 pi.
yes, 7 pi over 6. And then when I come over here and I'm looking at 2 pi, that's the same as 12 pi sixths. So when I come back 1, what's this radian measure?
11 pi.
Yes. Now, the same idea does hold true for the other ones, but it doesn't start with pi over 6. When I'm talking about these 45-degree angles, I'm going to say 45 times pi over 180, which comes out to pi over 4. So this first one is pi over 4. And now I'm thinking about this pi in terms of fourths. So that's the equivalent of 4 pi over 4. Which means when I go 1/4 back from that, what's the radian measure for this red part? Yep, 3 pi fourths. And then if I add 1 to 4 pi fourths, what's my radian measure here? 5 pi fourths. And over here, if I think about a double pi, 2 pi, as 8 pi fourths, this one is 1/4 short of that. 7 pi fourths. And then we can do the exact same thing with 60 degrees. We translate 60, first of all, times pi over 180. That gets us pi thirds, pi over 3. So this is pi over 3. Question? How is it 0 or 2 pi? Okay. So if I know that 60 degrees is pi thirds, pi over 3, then when I come over here, I think about pi as, yep, 3 pi over 3, and I subtract 1/3, and I get 2 pi thirds. And when I come down here, I'm taking that 3 pi over 3 and adding another one, which makes it, someone new? You're not new. All right, this last one. Yes, because this is 6 pi thirds, subtract 1, and we get 5 pi thirds. All we've got left is the same thing with the 90 degrees. 90 degrees, times pi 180 is equal to pi over 2. So 1/2 pi, 2/2 pi, which is pi,
Yeah.
3/2 pi, 3 pi over 2. And then this is the same as 4/2 pi. And look at that, you've completed a unit circle. How do you feel about it? 5. I could actually do this. Yes, it took us a couple of minutes, but I could do it. 3. I followed along and I couldn't follow along in the future and no sense of it, but I can't initiate that. 1. I don't understand. You guys came in late, so you missed some of the intro. That might explain some of the lower scores. So I'll come back to you in a minute. Now, what can we use this for?
Angle.
Do you remember SOHCAHTOA? What's that all about? Leo. Hold on, Leo. Boy, you must have had a really good geometry teacher, huh? Yes, so this allows us to create relationships between angles and sides in triangles. And I know you guys don't think this, but somebody who never took geometry might look at this and say, if I know that the side opposite 30 is 5, the side opposite 60 is twice as big because this angle's twice as big, so this one should be twice as big, 10. And this is 90, which is 3 times as big, so this should be 15. Can you see how somebody might think that? It means that they're linear and they're related that way. But that's not true. In fact, if the hypotenuse is 15 and these two add up to 15, this doesn't even make a triangle. That's just another line right on top of it. So it turns out that sine, cosine, and tangent allow us to translate between angles and side lengths. And it's not linear. If I take this sine as a function where this is the degrees of the angles and this is the ratio of the sides, what we see is that it works like that. If I look at my circle here, when I'm all the way over here, sine, first of all, is opposite over hypotenuse, right? We just said that sine is the opposite over the hypotenuse. So let's put the sides in the way we know they are. So what would be the sine of this 30 degrees?
5.
Good. So this would equal 5 over 10, which I could reduce to 1/2. And it turns out that's the same, no matter what triangle I'm dealing with. If I make this 3 and this 6 and this 3 root 3 over 2, the ratios are going to be consistent. So the sine of 30 will still be 3 over 6, which is 1/2. That's what the unit circle gives us. When I set this hypotenuse equal to 1, a unit circle, that means that the sine of 30 degrees is just equal to the y value. Sine of 30 degrees is 1/2.
I have a question.
Okay.
It's like kind of off topic, but like, could you, if you have like 1/2 over 1?
Yeah.
It's still technically half, so you reduce 1/2 over 1 to 1/2.
Yes, 100%. And that's exactly why we have a unit circle here, because if these hypotenuse are equal to 1, we don't need to worry about that part. In this triangle, the sine is just the opposite side. So come down here to the bottom and see where it says express the values in terms of x and y. The sine of theta in this unit circle is always equal to the y value of the coordinate that you write there. The cosine then, remember cosine is adjacent over hypotenuse. So in this little triangle up here, the adjacent side is the x divided by 1. So the cosine of theta is equal to x. And if the tangent is equal to opposite over adjacent, good, tangent is equal to y over x. Now, what that means is if I want to evaluate sine of 30, all I have to do is look on my unit circle for 30 degrees. There it is. It's this triangle. It stops here. This is the thing I care about. And then I'm saying sine. The sine is y. So my y is 1/2. So the sine of 30 is 1/2. What about the cosine of 5 pi over 3? Step 1. Find 5 pi over 3 on here. Which quadrant is it in?
Quadrant, 1/2.
1, 2, 3, 4. It's down here. This is the point I'm thinking about. And I'm looking for cosine. Is cosine x or y? It is x. So what's the cosine of 5 pi thirds? 1/2. Would you guys please independently and talk to your neighbors, figure out what the tangent of 7 pi sixths is? I'm going to walk around and check. Okay, as I circulate around, people are generally doing pretty well with this now. So to find tangent of 7 pi sixths, I'm going to find my coordinate of 7 pi sixths right here. The tangent of it means I'm taking my y over my x. So what I'm really writing is negative 1/2 over negative root 3 over 2. But now I have to rationalize that. Why? What's wrong with this that tells you you have to rationalize it? Excellent. There's a root in the denominator. And it's a fraction divided by a fraction. So I would personally choose to do it as negative 1/2 times negative 2 over root 3 first. Copy, change, flip. Right? Dividing by fractions is the same as multiplying by the reciprocal. So my 2's cancel, my positives cancel, and I get 1 over root 3. Now we're back to what Shelby said. We need to have a way to get rid of the radical in the bottom. And so I get root 3 over 3. That should be my solution for tangent of 7 pi sixths. Okay. That's how we use the unit circle to find sine, cosine, tangent of important values. They have to be these values, right? Multiples of 30, multiples of 45, multiples of 60. For now, that's all we can do. Could you use the unit circle to find sine, cosine, tangent of these values? 5, I think I could. 3, if I had these notes to remind me which one's x, y, and I had a unit circle, I could totally do it. It's 1. And hold on just 1 second. Okay, so step 1 is I need you guys to be able to create the unit circle. And that's as slowly as it takes you to do it is fine. Step 2 is using the unit circle, you should be able to evaluate things like cosine of 2/3, tangent of 1 pi over 6, whatever it is. I think we've demonstrated that. We're going to be getting into some things that are more. And so we're going to now talk about some properties of trigonometric expressions. First thing we want to talk about is, have you guys ever seen this graph before? Do you see this in advanced algebra? What this says is that, oops, the graph is sinusoidal. It is cyclical. It goes up to a value and then it comes down to a value. And it goes up to a value and it comes down to a value. And we can actually look up on the board here. This isn't so good for those on the screen. Take a look at 30-degree angle, pi over 6. The opposite side is really tall. When I go to pi over 4, this is the adjacent side. So this is the adjacent side, it's really low. Then the adjacent side gets shorter, adjacent side gets shorter. When we get to pi over 2, this is moving up and up and up to make a triangle. The adjacent side goes into 0. And then it begins becoming negative value.
And with the x value, we're talking about the cosine. With the y value, we're talking about the sine. So I want you to visualize that I'm drawing the unit circle right now. Here's the 0 line. And I go up to 30 degrees. This is my 30-degree opposite, right? This is a 30-degree triangle. The opposite side is 1/2. And that's why the sine is 1/2 of 30 degrees. As I move up to 45, what's happening to my line? It's increasing. What's happening at 60 degrees? Increasing again. What happens at 90 degrees?
It's back.
It peaks, it gets 1. It's the same as its hypotenuse. And then what happens? Oh, a little smaller, little smaller, little smaller, until it goes negative. This is the sine curve, which says it grows up until 1, comes back down until it hits 0, and then it goes negative. This curve is super important. You know why? Well, you heard of AM and FM radio.
Yes.
Sound waves travel like this. And as they travel, they impact things and they lose signal, they break down. But if you're trying to travel long distances, like out in the country, you want to use what's called AM radio, where the amplitude of it has been modified. AM modification. Amplitude modification. And that allows these big, tall waves to travel long distances without being broken down. But when you're in the city and you're trying to get noise, quote unquote, through these objects all over the place, you need to modulate the frequency instead. How quick it's spinning, how quick it's changing. That's why it's FM radio, frequency modulation. So it travels better in the city. So theoretically, use your AM stations when you're out in the country, and use your FM stations when you're in the city. That's why they're like that. Light travels as waves. And all of these waves can be represented by sine, cosine, and tangent curves. Now, if I draw a sine curve, as expected, it's cyclical. It looks like this. If I draw the cosine curve, it's the same shape, but it's a little bit adjusted, isn't it? How are they different? Yeah, I guess I drew it that way, didn't I? But this actually finishes a cycle in 2 pi, and so does this. They have the same frequency. Yeah, Anthony? Anthony? Good. This one starts at a 0 point, and so at 2 pi it ends at 0. This one starts at a high point and ends at a high point. And that makes sense because when I think about a unit circle, my first thing shows me that my x value is 1, so my cosine starts at 1, but my y value starts at 0, so my sine starts at 0. But here's something of interest. Let's say that I look at pi over 6, and I want to compare the sine of pi over 6 to the cosine of pi over 3. Look on your unit circles, please, and find the sine of pi over 6.
Here too.
Sine is what? X or Y? Sine is Y. So that's 1/2. What's the cosine of pi over 3? That's the x value.
1/2.
Also 1/2. So let me phrase that a different way. If I take a triangle and I call this angle theta and this angle alpha, in other words, they don't have numbers, I just got Greek letters in there. And I call this A, B, and C. What's the sine of theta? SOHCAHTOA. Opposite over hypotenuse, be A over C. What's the cosine of alpha? So now I'm looking from this perspective. Cosine is adjacent over hypotenuse. So it'd again be A over C. So what that tells you is that if you take the sine of an angle it will be the same as the cosine of the other angle that adds up to 90. In other words, if I tell you that the sine of 10 degrees is 0.13, what's the cosine of 80 degrees? Don't these two both add up to 90? Because this is already taken up with 90 out of a 180. These two are complementary. So this is also going to be 0.13. I just made it up. Let's see if I'm even close. It's 0.17. Okay, let's do another one. Let's say that I said, I know that the sine of 20 is equal to 0.34. What's the cosine of 70?
0.34.
0.34. In other words, the sine of an angle is always equal to the cosine of 90 minus that angle, right? So what you're going to find is on the backside of what we just did with our unit circle, I've got a bunch of these identities. And what I'm just pointing to now is something called co-function identities. The sine is equal to the cosine of 90 minus that same angle. Pi over 2 is 90. These co-function identities, you need to memorize. You need to put them on flashcards and memorize them. You also need to learn and memorize these, the reciprocal identities and the quotient identities. Now, some of these things you've never seen before, which is fair. We're in a new course, so we're not just taking what you learn in advanced algebra, we're doing something more. So if the sine is opposite over hypotenuse and the cosine is adjacent over hypotenuse and the tangent is opposite over adjacent, we're now going to introduce 3 new trig functions, but they're just these things flipped over. This one is called CSC, which stands for cosecant. And it's just going to be the opposite of sine. So it's H over O. And then cosine has a reciprocal of secant. So what do you think secant of theta is equal to?
Opposite cosine.
Okay, which would be what? H over A. And then cot or cotangent is equal to what? A over O. Good. So what you'll see is these reciprocal identities allow you to say that sine is 1 over cosecant and cosecant is 1 over sine. They're reciprocal functions. Cosine is 1 over secant. Secant is 1 over cosine. Now, if tangent is opposite over adjacent, isn't that also the ratio of these two? Couldn't I say opposite over hypotenuse divided by adjacent over hypotenuse, multiply times h over h, and I get O over A? So in other words, tangent of theta is equal to sine of theta over cosine theta. That's called a quotient identity. And then cotangent, which is the upside down of that, is the upside down of that. Last ones. So here's a right triangle. I've labeled the angle theta and the opposite side, the adjacent side, and the hypotenuse. And do you agree that I could do the Pythagorean theorem with these sides? If these are side lengths, I can do the Pythagorean theorem. So O squared plus A squared equals what? H squared. Now I'm going to do a little fancy math. I'm going to divide both sides by H squared. I'm allowed to do that, aren't I?
Yeah.
Okay. So what's H squared over H squared? and O squared over H squared, do you agree that we can treat that as O over H squared? And this is A over H squared. What is O over H? So that means that the sine of an angle plus the cosine of an angle squared is equal to 1. Every single time. This is an identity. It's always true. So, for example, if I told you that the sine of theta was 1/3, and I ask you to find the cosine of theta, and I tell you that theta is in quadrant 2, do you agree that this is not on our unit circle? So I can't look at my unit circle and find where it equals that value. But I can use this. If the sine of theta is 1/3, I can plug that in and say 1/3 squared plus cosine squared equals 1. 1/9 plus cosine theta squared equals 1. I'm going to subtract 1/9, and so I'm going to get 8/9. Then I'm going to take the square root. When I do the square root, I'm going to do plus or minus, and I'll talk about that in just a second. And then I can simplify this. Plus or minus root 8 over 9 is the same as plus or minus root 8 over root 9, plus or minus 2 root 2 over 3. So in other words, I know that the cosine is either plus 2 root 2 over 3 or minus 2 root 2 over 3. How could it possibly be two different values? Well, I'm going to draw what looks like the unit circle. It's not actually the one we just drew, because what we know is that this opposite side is 1/3. We're looking at whatever angle this theta is. And what I just found is that when the y value is 1/3 on this circle thing, I can have either a positive 2 root 2 over 3. Couldn't I also have an angle over here that also has a 1/3 y value? And that would be a negative 2 root 2 over 3. Those are the two places where the sine of theta equals 1/3. It's not drawn to scale. I don't know what it is. But since I was told that this was in quadrant 2, which value should I pick? The negative 2 root 2 over 3 or the positive 2 root 2 over 3? Negative. Good. So that's one of the ways that we're going to use the Pythagorean identity, which is also listed down here. And then we've got 2 more versions of that. I'll just derive those for you, and that's it for today. Actually, one more piece. So if I take sine squared theta plus cosine squared theta equals 1. By the way, notice when I write this, where's the square? On the sine part, I don't want to write it as like sine of theta squared, because I'm not squaring the angle. I could write it with the parentheses there, but this is easier and faster. I'm going to do some more magic math. I'm going to divide both sides by sine squared theta. Is that valid? Okay. Which gives me 1 plus cosine over sine is cotangent. What's the reciprocal of sine? What's the reciprocal of sine? Cosecant. So this is a second Pythagorean identity. If I gave you the cotangent squared, you could find the cosecant squared this way.
Cotangent squared is 1.
Yeah. Isn't that weird? The sine squared of theta plus cosine squared theta equals 1. If I divided both sides by cosine squared, hang in there, guys, we're almost there. This says that if I take the tangent squared and I add 1, I'm going to get the secant squared. So this is a third Pythagorean identity. Now, last thing. Do you remember even and odd functions? This is a good review because you'll be doing the final exam in what, 3 weeks? So what makes something an odd function? Is that an odd function? Okay, so is this an odd function? Is this an odd function? Actually, that one is. What about this? Now, you may have forgotten this, so let me refresh your memory. The way we test is we write it in F. Please watch this. This is going to help you in your final too. F of x is equal to this. I've changed the y into f of x. And what I do is I find out what happens if I put a negative x in. If I put a negative x in, negative x cubed, the negative stays. It becomes negative x cubed. If I put a negative x here, it becomes minus x. It doesn't affect the plus 3. And then the third thing I do is I distribute a negative across the whole function. So distributing a negative across this makes negative x cubed. Distributing across this makes negative x. Distributing across this makes negative 3. If I find that these two end up the same, like for example, and then if I did like f of x is equal to x squared, f of negative x is equal to x squared, negative f of x is equal to negative x squared. When I find that these two match, what kind of function is it? Even. When I find that these two match, what kind of function is it? Odd. When I find that nothing matches, it's neither. Remember that? You also might remember that odd functions have symmetry over the origin, whereas even functions have symmetry over the y-axis. It turns out that when I look at the sine curve, does it have symmetry over the origin or over the y-axis? So over the origin, it doesn't reflect this way and look the same. It has to spin around 180, just like this one. But if I do the cosine function, it flips over the y-axis. So that means that the sine function is odd and the cosine function is even. So that's what's down here. If the sine of negative theta is equal to negative sine of theta, that means this is odd. Whereas if the cosine of negative theta is equal to the regular cosine of theta, that means it's even. So this one is odd. This one is odd. This one's even. This one's odd. And let's look at something else about this. If I take an angle some theta, and let's say that this is theta, and this coordinate is x comma y. What's the cosine of theta? Cosine is x or y? It's x. So what's the cosine of this angle then? X. Now, what if I took the cosine of negative theta? In other words, instead of going up this way theta degrees, I went down this way. Is it? It's still x, isn't it? Look at this picture. If I go down, my x value stays the same. It's still in the positive direction. That's why cosine is even. But if I do sine, here's theta. This is xy. What's the sine of theta? Sine is y value. So what's the sine of theta? Okay. And then I do a negative theta. What's this value going to be? Negative y. That's why this one's odd. Okay. Tonight, your homework is in Pearson, and it's going to spiral through some of the stuff you did last class with arc length and angular velocity and linear velocity. And then it's going to get into some of this stuff with the unit circle. Oh, sure. If the sine of theta is equal to y, and cosecant is the reciprocal function, one over y. And if the cosine is x, the secant is going to be, yep. And if the tangent is y over x, the cotangent is going to be x over y. All right. Thank you all for your attention. I know that was a lot.